Hello everybody. In this video we're going to talk about continue the topic of the continuity equation, and in this video we are going to talk about some of the special cases of the continuity equation. But before we talk about these special cases, I would like to go back to the continuity equation because there is one point I want to highlight before we go through the special cases, and this is a point that's related to the terms that we have here in this equation. So if I zoom in here, you would see that we have four terms, and these four terms are results of the derivation that we made from the very beginning of this chapter. And this term, which is the R term, is the reaction. This is the time dependence, which represents the unsteady state behavior of the system. And this was originally the flux term, which was in minus n out divided by the distance, and we replaced this term with these two terms. And these two terms were discussed earlier in chapter 22, and we mentioned that this term represents the flux due to the concentration gradient, and this is the flux due to the bulk flow. So this is what we translated into this term, and this is what translates here into these two terms. So this term is the flux due to the concentration difference, this is the flux due to the bulk flow, this is the unsteady state term, and this is the rate term. So these are the points that I want to highlight, because when we talk about the special cases, we will cancel some terms, or we'll put some terms equal to zero. And the reason we are doing this, because our understanding of the system, and this will highly depend on the understanding or our understanding on the significance of each term of these terms. So now let's go for the special cases of the continuity equation, and we have four famous special cases. The first special case is when we have constant diffusivity and constant density. Constant density means that we have an incompressible fluid, and from fluid mechanics and from Navier-Stokes equation we can tell that for incompressible fluids the gradient of velocity is zero. And this is what we can use in this equation. So this term needs to be expanded, and we can expand it to rho del dot v plus v del del rho a, and then we know that del dot v equals 0, and we here took the rho and dAB out of the gradient, so it is now the second order gradient of the omega of the mass fraction. And this is how the equation will look like. We'll just put the terms that are with the same sign on each side. So the negative terms, I put them on the other side, and these are the positive terms. And we can use, of course, the same for the molar units. So this is the first special case. The second special case is when we have the same conditions with no reaction. So simply we will put the reaction term equals to 0. So this is getting more simpler now. The third case is for the same thing, but we will have static flow, meaning that we don't have any bulk flow. So the term of the bulk flow, which is the v dot del rho a, is the bulk flow term. So this is going to be 0, so we will end up with just these two terms, and this is if we are using molar units. This equation is very famous for its name of Fick's second law of diffusion, and that's why we differentiate between them by saying that the first one was the Fick's first law, and this is Fick's second law. And you know, this makes sense because we don't have reaction in first law. We don't have reaction. It is constant density and constant diffusivity, exactly like what Fick's first law states. So it is almost under the same conditions, but this is more general. There is an unsteady state term here, and it can be used for much more cases than the Fick's first law. The last case, if we have unsteady state steady state diffusion. So in this case, the time dependence term will be equal to 0. So these are the special cases of the continuity equation. One thing that I would like to mention regarding the continuity equation is that we have been discussing it since the very beginning when we started the derivation using the Cartesian coordinates. But we mentioned before that we can be operating under spherical or cylindrical coordinates, and in this case we need to use the equation, the continuity equation, in these coordinates. So the way we do this is, we are not going to do the derivation because it's going to be the same but with the another coordinate system, so it's going to be repeating the same thing with just some differences. But this is how the equations are. This is in the for Fick's second law, in rectangular or Cartesian coordinates, and cylindrical coordinates, and spherical coordinates. Of course, the Cartesian is the most simple form of the equation compared to the cylindrical and the spherical coordinates, of course. And for the general equation or continuity equation, this is how the equation will look like. This is in terms of the flux, in terms of n. Anyway, so this is the shape of the continuity equation in the different coordinate systems. I can tell that whoever is watching this video now might be thinking of some questions, or there are some questions that are jumping into his or her mind, which are related to how can we deal with these equations. And this is a very legitimate question, actually, and I can totally understand that this is something that you're thinking of, and this is what we will be trying to answer in the next couple of videos. So we will discuss first the information that we need to know so that we can solve this equation, and then the strategy of solution, or the steps that we need to follow so that we can get these equations solved in a way or another. So we will continue in the next video, so I'll see you then, inshallah. Goodbye.